Hello AP Chemistry, and welcome to a little bit of math where we start adding strong acids or strong bases to our buffer system. So first of all, buffer has to be composed of specifically a weak acid and its conjugate base, right? Or likewise we could have a weak base and its conjugate acid, right? Or I guess we could write that the other way, right? We could have a weak base and its conjugate acid, right? Either way, we have to have both species present, right? If we add strong acid, right, strong acid, we will consume some of the base and produce some of the acid, yes? And then we'll calculate new values, and then we'll figure out our new pH, yes? Likewise, if we add a little bit of strong base, we'll consume some of the acid, produce some of the base, and we'll calculate new values, right? That's all this diagram is designed to show you, right? Which is, again, a reiteration of what we talked about previously. So here, if we take a look at this figure, right, things to take note of, right, the purpose of a buffer is to resist changes in pH. So here, right, this figure is just showing you that if we have a 1 liter buffer that's 0.3 molar acetic acid and 0.3 molar acetate, and we add a little bit of strong base, the pH changes very little, right? The pH changes by less than 1/10 of a pH unit, okay? Whereas if we were to add 5 mils of 4 molar sodium hydroxide to pure water, right, we go up approximately a lot of pH units, right? So 5 pH units, right? And that's because at that point, right, this completely dissociates, right, and completely governs our pH. Where here it dissociates, but it is consumed, right? And that ratio of acid to base doesn't change significantly. And as long as that ratio doesn't change significantly, neither does pH. Yes? All right. Let's go ahead and try a practice problem. So, determine the pH of the original buffer described in sample exercise 17.5 after the addition of 0.02, I think this is supposed to say moles, yep, 0.02 moles, and the pH of the solution that result from the addition of 0.02 moles of HCl to pure tap water. So, first let's talk about this one. This one's easy, right? If I add 0.02 moles of HCl to 1 liter of pure tap water, right, that's 0.02 moles of HCl in 1 liter, right? Which means that's my molarity of HCl. Now, how do we just do this pH in our head? Let's approximate this pH. Right, this in scientific notation is 2 times 10 to the negative 2. Yes? All right, pH means taking the negative log of this, right? Negative log base 10 of that, right? Which means, right, what do we do? Right, it means that our pH is ballpark 2. Yes? Does that make sense? As in this comes down and ends up over here. Yeah? Okay. So anyway, ballpark pH of about 2, a little bit less than 2. Over here, let's go look at our original buffer. So you have a buffer that consists of 0.3 moles of acetic acid and 0.3 moles of sodium acetate. Now, is this sodium component important? No, right? What really matters, right, is that we have our acetate ion and that the sodium ion has no effect on pH, right? Negligible in terms of pH. Okay, and we have a 1 liter solution, and we have our original pH. All right, so we know that we have 0.3 moles of this and 0.3 moles of that, and we're adding strong acid, okay? So if I take my HCl, right, what's my HCl going to consume? Right, this is a strong acid. It's going to consume the base component, right? And if it's helpful to you, go ahead and label them, right? This is my weak acid, and this is its conjugate base, right? So it's going to react with the base, which means that this is going to be, and again, strong acid, so it's completely dissociated, so it's going to completely react with whatever of this it needs, right? And this is going to form some CH3COOH, and it's going to form some chloride ion, which is, again, inconsequential to our pH. So here, if we have, so we have, what do we have? 0.02 moles of HCl, right? So 0.02 moles of this, okay? And we have a total of 0.3 moles of this. Yes? Does that make sense? Okay. And originally, how much of this do we have? Right. 0.3 moles, right? And this is irrelevant. All right. So then we know that this is going to react completely, right? Complete dissociation. So minus 0.02 moles, right? Here, minus 0.02 moles. Here, what happens? Right. Plus 0.02 moles, right? Which means that none of this is left, right? So none of that's left to affect our pH. Here, if I subtract 0.02 from this, what do I end up with? right? 0.28. Here I end up with 0.32, right? Okay, so then I take all of that, and we're going to put it back into our original pH discussion equation, right? So we know that Ka, let's go down here, Ka is equal to my A minus times my H3O plus over my HA, right? And what part of this are we looking for? We're looking for the pH, right? So this is basically what we're solving for. So let's plug in all the pieces that we know, right? So we know that our Ka is, I think it's 1.8 times 10 to the negative fifth, is equal to my A minus, which is this component, right? 0.28 molar times my H3O plus over my HA, which is 0.32 molar, right? And then I just solve for my H3O plus, and then I would take the negative log of that. Yeah, does that make sense? Okay, and then if instead this were a strong base that we were adding, like sodium hydroxide, it would consume what? Right, it would consume the acid and produce the base, right? But it's all the same idea, right? If we take from one, we add to the other. Yes? All right, make sure this makes sense. Be good, and I will see you soon. Thanks for listening. Bye.